In this video, we're going to talk about the relationship between the carrier concentrations to that of the Fermi energy level. And in our previous videos, we have derived the relationship between carrier concentrations to the Fermi energy level, where electron concentration is given by Nc times e power minus of Ec minus Ef over kT, and hole concentration is given by Nv times e power minus of Ef minus Ev over kT, where we know that Nc is the effective density of states in conduction band and Nv is effective density of states in valence band. So in band diagram, the bottom edge of the conduction band is called Ec and the top edge of the valence band is called Ev. For our understanding, so let me take the Fermi energy level to be somewhere here. Then the electron concentration basically depends on the difference between Ec to Ef. So the difference is Ec to Ef. So this is Fermi energy level, I'm assuming. And now at the same time, the whole concentration depends on Ef to Ev difference. And that value is this distance, Ef to Ev. And we know the relationship between the electron concentration in conduction band to that of the whole concentration in the valence band is related by the mass action law, which is given by N times P is equal to Ni square, which means the Fermi energy level for a given semiconductor is same for calculation of both electron and hole concentrations. Now to understand what happens when Fermi energy level changes, now let me take the Fermi energy level for next case to be slightly, let's say, below the first case. To distinguish this, let me take the first one to be EF1, now the second one to be EF2. So in this case, the second case where the EC to EF is basically higher compared to the previous one. So what happens is this expression, the exponential here, would be smaller for the second case compared to the first case. So let me write it here. EC minus EF1 would be smaller compared to EC minus EF2. So we can say the exponential there, which is EC minus EF over KT with respect to, so this is for EF1, EC minus EF2 over KT, the relationship would be like this. This would be greater. And for both the cases, the Nc is assumed to be constant. So we can say the electron concentration in first case is greater compared to the second case, which tells us that if the Fermi energy level is closer to the conduction band edge, which is Ec, then the electron concentration is higher. And similarly, we can talk about hole concentration, where Ef minus Ev in first case is higher, and in the second case, it has reduced. So similarly, we can talk that EF1 minus Ev is basically greater than EF2 minus Ev. And similarly, we can say e power minus of EF1 minus Ev over KT relationship to e power minus of EF2 minus Ev over KT would be this way, where in the second case, the whole concentration would be higher because the distance between the EF2 to EV is smaller compared to EF1 to EV. Now this clearly indicates that as we increase the Fermi energy level from EF1 to EF2, what is happening is the electron concentration is basically decreasing. So we can say as we move EF closer to EC, let's say, then electron concentration would increase and hole concentration would decrease. If EF is moving closer to EV, which means moving away from EC, electron concentration would decrease and hole concentration would increase. But in both of the cases, the product of N and P would always be satisfying the mass action law, which is Np is equal to Ni square. Now here we are talking about two references, which is EC and EV. There is another way of representing this electron concentration and hole concentration in terms of the intrinsic Fermi energy level. So that is more convenient, and we will use that extensively in this course. So let us see that particular expression. These expressions for intrinsic semiconductor can be written as N is equal to Nc times e power minus of Ec minus Ef. The Ef for intrinsic semiconductor is called E suffix I, representing intrinsic semiconductor's Fermi energy level. And for P, we can write Nv times e power minus of Ei minus Ev over Kt. And both of them are equal to Ni. We know in intrinsic semiconductor, N is equal to P equal to Ni. We can rewrite this expression for electron concentration as N is equal to Nc times e power minus of Ec minus Ef. And we can add Ei and subtract Ei so that the equation doesn't change over Kt. And this can be rewritten as Nc times e power minus of Ec minus Ei over Kt times e power Ef minus Ei over Kt. So we can rewrite this expression as N is equal to Ni times e power Ef minus Ei over Kt, where we have taken this Nc times this exponential as Ni. We can get this from this equation. Now similarly, for the whole concentration in valence band, we can write it as Nv times e power minus of Ef minus Ev. We can add Ei and subtract Ei over Kt. And we can write this as Nv times e power minus of Ei minus Ev over Kt times e power Ei minus Ef over Kt. And we can write this as P is equal to Ni times e power Ei minus Ef over Kt. So now we have the two expressions in terms of ECEF and EVEF, whereas here we have the electron and hole concentrations in terms of EF and EI, and hole concentration in terms of EF and EI. So let us understand these two equations in terms of the energy band diagram, where we take the bottom edge of the conduction band to be EC and top edge of the valence band as EV. Now our reference is no more the EC and EV, just like in the previous case. Now it is EI. The Fermi energy level is with respect to EI. So now EI is actually the Fermi energy level of intrinsic semiconductor. I'm taking it to be at the half of the forbidden energy gap, where this distance EC minus EF is called the EG. If the Fermi energy level is somewhere here, the distance between this Fermi energy level to EI is positive, which means EF minus EI is positive. So this exponential would be a higher value multiplying Ni, which means electron concentration would be a lot higher compared to Ni. Whereas at the same time, the whole concentration depends on the difference between EI to EF, which means EI minus EF would be a negative value. So if exponential of negative value would be a very small value, so multiplying Ni, we can say P is far less compared to Ni, depending on the difference between EI to EF. And we can see clearly, if you multiply N times P, we can directly get Ni square from these two expressions. So these expressions won't refer the Fermi energy level with respect to EC or EV, it refers with respect to EI. So both this set of equations, the first ones here and the second ones here, both represent the same thing but in a different way. And following our course in next videos, we will be using most of the time these equations. But when we do problems, we will be choosing either of it depending on which one is easiest to find the answer. Similar to previous case, let us compare when EF is above EI, we can say N is greater than P, and we have seen it. And if EF is below EI, we can say N is less than P. These equations can also be represented in this form, and these bottom equations can also be represented in this form. I've just rearranged them. Instead of writing in exponentials, I've written them in ln form, so that in some times the calculations would be easy if we substitute in this way.